In this video, we're going to look at Bronsted Lowrie acids and bases. So previously, we had looked at acids and bases, and we'd seen like, oh, if we have hydrochloric acid, the Arrhenius description is that you've got a hydrogen ion and a chloride ion. And that's just fine as long as it's a pretty straightforward acid. The modified Arrhenius acid explanation is that it reacts with water to make a hydronium and the anion. And that's a pretty good description as well. And so this is what we've done so far. Now, the reason that the Arrhenius description doesn't work is that there are some things like carbon dioxide, which if I put it in water is acidic. And so the carbon dioxide in water will make a hydronium, and what happens is the water is split into a hydroxide and hydronium. These make my hydronium, and this bonds to carbon dioxide to make HCO3 negative. And so this is an acidic solution. It's a weakly acidic solution, and so this is less than 50% forward reaction. And so we have a reason for having a modified Arrhenius description, but it's not perfect either. So what we're going to do is we're going to introduce you to Bronsted Lowrie acids and bases. And what we're going to do is we're going to now stop talking about acids and bases simply by does it make a hydronium or a hydroxide, although that's going to show up all the time. But we're going to follow what happens to a hydrogen ion. So we're going to get chemicals that donate the hydrogen ion are acids, and bases accept a hydrogen ion. So if I looked at hydrochloric acid reacting with water, you can see that this hydrogen ion reacts with this. So this is my donor, and this is my acceptor. And it produces hydronium, because this accepted the hydrogen ion, and this donated or lost its hydrogen ion and became chloride. And so we're going to start talking about things in the reaction as acids and bases. So here in this next reaction, we can take a look at water is donating its hydrogen because it produces a hydroxide, right? So the water becomes hydroxide, donates its hydrogen, and the ammonia gas, when it gains this hydrogen ion, becomes ammonium. So now water is acting as an acid because it's donating a hydrogen, and the ammonia is acting as a base because it's accepting it. And so now we're going to be able to redefine acids and bases as being proton donors, and hydrogen ion is called a proton. So the proton donor is the acid, and the proton acceptor is the base. So acids donate protons, bases accept protons. And we can look at these reactions in the forward and the reverse, right? So here, if I look at this reaction backwards, this is donating its proton here, right? So when it's going backwards, the ammonium is an acid and the hydroxide is the base. And so now we're going to be able to look at these equilibrium systems and say, what's the acid in the reactant? What's the acid in the base, right? So in this case, this was my acid in the reactants. This is my base in the reactants. But in the products, this is my acid and this is my base. And so this is going to allow us to describe things together. We're also going to get some things that we're going to call them acid-base pairs. And so we're going to describe that in a moment. But water can be a reactant. Note that the reactions above fit the modified Arrhenius theory from Chem 20, where water being a reactant helps describe why some chemicals are acids and others are bases. But they don't require water to be a reactant or even a product. So you can see here that my hydronium is donating its hydrogen, so it's the acid, and then the ammonia is going to be my base because it's accepting the hydrogen. So the ammonia becomes ammonium and the hydronium becomes water. So in any reaction where hydrogen ion goes from one aqueous reactant to another, that's a Bronsted Lowrie acid. The chemical that accepts it is the Bronsted Lowrie base. Now there are some chemicals that are called amphoteric. So amphoteric means experimentally it can act as an acid or a base. So if you take hydrogen carbonate ion, and you would get that from something like sodium hydrogen carbonate, AQ, all of that becomes sodium ions in solution and hydrogen carbonate. Well, that hydrogen carbonate, if it's in water, can act as a base because it's going to accept a hydrogen. So the hydrogen ion, the proton, goes to the hydrogen carbonate to make carbonic acid, and the water becomes hydroxide. You could also have hydrogen carbonate react with water, and this hydrogen here is going to be donated to the water, and so you end up getting water becomes hydronium, and the hydrogen carbonate, which was the acid, will become carbonate ion. So amphoteric species could accept or donate a hydrogen, and this is an empirical definition. So when I'm looking at this, I always look at amphoteric has an E. I won't ask you for the difference between amphoteric and amphiprotic because they are very comparable and they're just basically easy to confuse. Amphiprotic species is a chemical that theoretically could donate and accept a hydrogen. So the hydrogen carbonate is amphoteric if it's experimentally shown to act as an acid and a base, and it's amphiprotic if it just looks like it could be. Like it should be able to become donate a proton or accept a proton, and we will see a few examples of those in our data booklet. So in our data booklet, you're going to, I'll show you those another time. So in these questions, try to identify the Bronsted Lowrie acid and the Bronsted Lowrie base. We'll do the first one together. It's fairly obvious that this is donating a hydrogen, so that's an acid, and this is accepting a hydrogen, so it's a base. In the next one, this hydrogen is donated, so this is my acid and this is my base. Okay, so go through and make sure you can spot those. Do questions 3 and 4, please, and we'll catch you in another video for conjugate acids and bases.